The universe was not always a place of light. For hundreds of millions of years, it was a formless, silent ocean of simple gas, a profound darkness stretching across all of space. But then a revolution began. This was the Cosmic Reionization Era, a dramatic transformation that ripped the universe from its dark age and forged the transparent cosmos we see today. By the end of this journey, you will hold the keys to 25 of its greatest unsolved mysteries. We will confront the celestial powerhouses that first pierced the gloom and ask why some regions of space saw the light before others. What cosmic puzzle do you hope we finally solve? So what were these cosmic revolutionaries, the very first entities to flood the universe with light? The prime suspects are two very different kinds of celestial powerhouses. The first candidate is a generation of stars so ancient and pure that we have never seen their like since. Astronomers call them population 3 stars. These were not like our stable sun. They were leviathans, behemoths hundreds of times more massive, forged solely from the pristine hydrogen and helium that filled the infant cosmos. They lived fast and died young, burning with a ferocious, ultraviolet intensity that could have ripped the universe apart atom by atom. Their brilliant, short lives ended in colossal supernova explosions, seeding space with the first heavy elements and potentially clearing the way for more stable stars. The second suspect is even more extreme, active galactic nuclei. These are the raging hearts of the very first galaxies, where supermassive black holes, voraciously feeding on surrounding gas, became the brightest beacons in existence. The incredible energy released from these feasting monsters could have blasted out radiation powerful enough to ionize vast regions of space far beyond their own galactic borders. So which one was the true hero or villain of this cosmic transformation? Was it the collective fury of those first magnificent stars or the focused, piercing glare from the earliest black holes? Perhaps it was a messy, uncoordinated effort, a combination of both that gradually overwhelmed the darkness. The frustrating truth is that our most powerful telescopes are still straining to catch a direct glimpse of these elusive pioneers. They are like the founding figures of a lost civilization, their existence inferred from the world they built, but their true forms remaining just beyond our sight. But if we cannot yet see the architects of reionization directly, we can investigate the crime scene itself, piecing together the precise timeline of this universal transformation. When exactly did the lights first flicker on, and how long did it take for the cosmic fog to finally lift? This is our second great mystery. Data from powerful observatories like the Planck satellite and the James Webb Space Telescope paint a broad picture, suggesting this era of upheaval was largely complete by the time the universe was about 1 billion years old. Yet, pinning down the exact start and duration is a monumental challenge for cosmologists. Was it a swift, dramatic event, a sudden dawn that swept across the cosmos, or was it a slow, sputtering process with fits and starts over hundreds of millions of years? The evidence we have is maddeningly conflicting. The cosmic microwave background, the faint afterglow of the Big Bang, carries the scars of this epoch, telling us when it was mostly over. Yet, when we look at the light from ancient quasars and gamma-ray bursts, some of the most distant beacons we can detect, their signals tell a different story, one of a patchy and prolonged process. Settling on a definitive timeline is not just about dates on a cosmic calendar. It is the key to understanding the very nature of the first stars and galaxies, forcing us to ask whether they emerged in a single, brilliant wave or a slow, hesitant trickle that gradually overwhelmed the darkness. This transformation was anything but a uniform tide of light washing over the cosmos. Instead, picture a vast, dark ocean where the first lighthouses flickered on one by one, each one carving out its own sphere of influence in the surrounding gloom. These were the ionization bubbles, our third great mystery. Around each of those early, brilliant stars or active galaxies, the intense radiation acted like a cosmic blowtorch, heating and stripping electrons from the surrounding hydrogen atoms, creating a local, transparent zone. For the first time in hundreds of millions of years, light could travel freely again, but only within these isolated pockets. The universe was becoming a chaotic patchwork of light and shadow. As more of these power sources ignited, their bubbles began to grow, eventually bumping into each other and merging into ever larger transparent regions. Yet this was not a neat, orderly process. Sophisticated computer simulations reveal a messy and uneven cosmic dawn. Some parts of the universe, perhaps dense with early galaxies, became brilliant hubs of clarity relatively quickly. Other, more isolated regions languished in darkness for millions of years longer, their hydrogen gas still stubbornly neutral. This intricate topology, this cosmic quilt of light and dark, raises a profound question. What determined which parts of the universe saw the light first? Was it simply the luck of the draw where the first stars happened to form? Or were there underlying patterns in the distribution of matter laid down by the Big Bang itself that guided this entire process? Unraveling the map of this great reionization is like trying to decipher the growth of a sprawling civilization from only a handful of scattered ruins. While we chase the brilliant quasars and massive stellar leviathans, a quieter, more numerous suspect might have been the true force behind the cosmic dawn. The fourth mystery asks if the real work was done by countless faint dwarf galaxies. These are not the majestic spiral galaxies we see today, but tiny, fragile collections of stars, each 1,000s of times smaller and dimmer than our own Milky Way. Individually, their light was a mere candle flame in the vast cosmic dark. But what if there were billions of them? The faint galaxies hypothesis suggests that it was their collective power, the combined ultraviolet output from this unimaginable multitude, that ultimately flooded the universe and stripped the hydrogen atoms clean. This idea turns our search on its head. Instead of a few dramatic beacons, we are now looking for a cosmic chorus of faint voices, all singing in unison to illuminate the cosmos. The challenge is that these dwarf galaxies are at the very edge of what our most powerful telescopes can detect. They are like trying to spot a single firefly from miles away in a fog. For decades, they have been little more than a theoretical necessity, a ghost population we suspected must exist to make the math of reionization work. But did they? How many of these tiny galaxies were actually out there? And just how efficiently could their young, hot stars produce the specific, high-energy photons needed for ionization? The answers are locked in the deepest observations of space. Now, the James Webb Space Telescope is turning its incredible gaze toward this faint frontier. It is designed to see precisely these dim, ancient objects. Every new, faint smudge of light it discovers in the early universe is a potential piece of this puzzle. If Webb finds a veritable sea of these dwarf galaxies, it would completely reshape our understanding, suggesting that the universe's great transformation was not a story of a few giants, but of the collective power of the small and the numerous. Even the most brilliant galaxy is a prison for its own light. The fifth mystery of reionization asks a deceptively simple question. How did the life-giving radiation actually break free? This is the problem of the escape fraction, the tiny percentage of ionizing photons that manage to flee a galaxy's gaseous confines and travel into the vast emptiness between galaxies. If this number was too low, reionization simply could not have happened. Think of an early galaxy not as a clear sphere of stars, but as a dense, turbulent nursery of gas and dust. Within this chaotic environment, new stars are blazing, flooding their surroundings with the harsh, ultraviolet light needed to rip electrons from hydrogen. But that very gas and dust is the problem. It acts like a thick, cosmic fog, absorbing and scattering these precious photons long before they can reach the edge and stream out into intergalactic space. For a galaxy to become a beacon, it had to be leaky. So what cosmic conditions could pry open a window in that fog? Perhaps it took the explosive force of supernova, the violent deaths of massive stars, to literally blow holes in the galactic gas, creating clear tunnels for the radiation to escape. Or maybe it was the fierce stellar winds from those same stars, pushing the gas away and thinning the shroud from within. The geometry of the galaxy itself might have been the key. If the brilliant stars were not evenly distributed but clustered on one side, their combined fury could have blasted a directional jet of ionizing light straight out into the cosmos. Measuring this escape fraction for galaxies in the early universe is one of the most difficult challenges in all of modern astronomy. We are trying to detect something that, by its very nature, got away. It is like trying to measure the exact amount of water vapor rising from a boiling pot by only studying the pot itself and not the steam. The evidence is fleeting and indirect. Some observations suggest the escape fraction might have been as low as 5%, while others indicate it could have been 20% or more in certain ideal conditions. That difference is not a minor detail. It is the difference between a universe that remained forever dark and the transparent cosmos we inhabit today. The ultimate mystery is determining the exact, perfect recipe of stellar fury and galactic structure that finally allowed the universe's first light to flood out and begin its great work. Yet for all the power of stars and dwarf galaxies, another force was awakening in the darkness, one of almost unimaginable ferocity. The sixth mystery confronts the role of quasars, the intensely bright cores of galaxies powered by supermassive black holes in a feeding frenzy. As colossal amounts of gas spiraled into these gravitational monsters, the process generated a torrent of radiation so powerful it could outshine an entire galaxy. A single quasar was a prodigious factory of the very ionizing photons needed to clear the cosmic fog. But did their brilliance make them the lead actors in this cosmic drama, or were they merely spectacular supporting players? The answer hinges on a simple yet unresolved question of numbers. Were there enough quasars shining brightly enough, early enough, to matter on a universal scale? This question fuels a great debate among astronomers, often framed as stars versus black holes. In the star's first model, the collective output from countless galaxies, large and small, did the heavy lifting, with quasars perhaps only joining the party late to help finish the job. The black hole's first model, a more radical idea, suggests these brilliant beacons could have been the primary pioneers, igniting the first and largest ionization bubbles and setting the entire process in motion. Deep field surveys, where telescopes stare at a single patch of sky for hundreds of hours to gather the faintest light, are our key to solving this. They are a cosmic census, searching for these rare, brilliant objects in the universe's infancy. The results so far suggest that truly powerful quasars were too few and far between to shoulder the burden alone. But what if there was a hidden population of smaller, less brilliant active black holes, their contributions overlooked because they are so much harder to find? Their combined output could have been significant, like 1,000 embers adding up to a formidable fire. Quantifying the true impact of these cosmic monsters means peering into the hearts of the very first galaxies, trying to distinguish the light of their stars from the potential glare of a hungry, central black hole. It forces us to ask whether the universe was illuminated by the steady glow of stellar birth, or if it was first pierced by the focused, piercing glare of gravity's ultimate triumph. The very space between galaxies holds a secret history of this transformation, written not in light but in shadow. This is our seventh mystery, the state of the intergalactic medium, the vast and nearly empty cosmic web of primordial gas. To understand reionization, we must probe this invisible ocean to learn its structure, its density, and its temperature. How do we study something so diffuse and dark? Astronomers use the brightest objects in the cosmos as cosmic flashlights. They train their telescopes on the brilliant light of distant quasars, As that light travels for billions of years across the universe, it passes through this intergalactic gas. Specific wavelengths of the quasar's light are absorbed by the neutral hydrogen atoms it encounters along the way. This creates a unique pattern of dark lines in the quasar's spectrum, like a barcode imprinted by the universe's fog. By reading this barcode, scientists can use it as a cosmic dipstick. They can measure how much of the gas was still neutral at different points in cosmic history and how that changed over time. The mysteries these absorption lines reveal are profound. Was the intergalactic medium a smooth, uniform soup, or was it incredibly clumpy, with dense filaments of gas weaving through vast, empty voids? The answer dictates how reionization proceeded. Ionization bubbles would have grown more easily through smooth, uniform regions, but a clumpy medium would have been a tougher opponent, with dense knots of hydrogen stubbornly holding onto their electrons for longer. Furthermore, the temperature of this gas is a vital clue. As the first ultraviolet radiation flooded through it, the gas would have heated up dramatically. Tracking that temperature rise tells us about the timing and intensity of the ionizing radiation itself. Was it a sudden, searing heat wave or a more gradual warming? Unraveling the precise conditions of the intergalactic medium is an immense challenge, like trying to map the chaotic weather patterns of the entire infant universe from a handful of scattered sensor readings. Each new quasar we observe adds another data point, slowly revealing the intricate topography of the cosmic battlefield where light fought to conquer the dark. Buried within the light of the most distant quasars is a ghostly forest. This is the Lyman Alpha Forest, a dense collection of dark absorption lines in a quasar spectrum, and it is our eighth great mystery. Each of these lines is the shadow of a single cloud of neutral hydrogen gas, a wisp of the primordial universe that the quasar's light passed through on its multi-billion-year journey to our telescopes. This forest is a fossil record, a direct snapshot of the intergalactic medium at a specific moment in cosmic history. The mystery lies in how this forest evolved. As the fires of reionization spread, the ultraviolet radiation from the first stars and galaxies would have systematically burned away these neutral hydrogen clouds, ionizing them into transparency. One by one, the trees in this cosmic forest should have vanished. The key is that this did not happen everywhere at once. When astronomers look at the spectra of quasars from slightly different cosmic epochs, they see a dramatic transformation. In the very earliest, most distant quasars, they sometimes find something startling, not a forest, but a vast, empty clearing called a Gunn-Peterson trough. This complete absence of certain absorption lines indicates that the light has traveled through a region so saturated with neutral hydrogen that every last bit of the relevant wavelength has been absorbed. It is the spectral signature of a universe still deeply shrouded in fog. Yet, look at a quasar from a few 100 million years later, and the forest is back, though thinner, showing that the process of ionization was well underway, clearing some regions but not others. Decoding this complex pattern is like trying to read a history of a great deforestation from the scattered stumps that remain. The profound question is why the troughs appear so starkly in some data and not in others. Does this mean reionization was incredibly patchy, with some vast voids remaining neutral long after other regions had become clear? Or are we misinterpreting the shadows, our view obscured by the very complexity of the process we are trying to measure? This forest of shadows is our most detailed map of the reionization epoch, but its trees are phantoms, and their disappearance marks the precise moment the universe became transparent. Peering back into this era is like trying to hear a whisper from across a roaring stadium. The observational challenges we face are as immense as the cosmos itself, forming our ninth great mystery. Why is it so phenomenally difficult to see the epoch of reionization directly? The first and most fundamental obstacle is distance. The light from the very first galaxies has been traveling for over 13 billion years to reach us. Over that unimaginable journey, the expansion of the universe has stretched the light waves themselves, shifting them from the visible spectrum all the way into the infrared. Our eyes cannot see this light, and even most of our telescopes are blind to it. This is the cosmic redshift, and it forces us to build entirely new kinds of eyes, instruments sensitive to these specific long wavelengths. But the problem runs even deeper. We are trapped in a cosmic catch-22. The very neutral hydrogen that defined the Dark Ages acts like a dense fog, absorbing the energetic ultraviolet light from the first stars and galaxies. The very signal we are desperate to see is being swallowed by the medium we are trying to study. So how do we overcome this? The answer lies at the bleeding edge of technology and human ingenuity. The James Webb Space Telescope was specifically engineered to solve the redshift problem. Its giant golden mirror and ultra-sensitive infrared instruments are designed to catch that faint, stretched starlight, allowing it to see the galaxies whose light began its journey during reionization. But to probe the hydrogen fog itself, we need a different kind of tool altogether. The upcoming Square Kilometre Array, or SKA, is a revolutionary radio telescope that will not look for light, but will listen for a faint, specific radio signal emitted by the spin flip of neutral hydrogen atoms. Mapping this signal will let us create a three-dimensional chart of the cosmic fog, showing us precisely where it was and when it began to clear. Until these tools are fully operational, scientists rely on clever, indirect methods, using the shadows in quasar spectra and the subtle glow of cosmic background radiation to piece together the story. The mystery of reionization is not only a puzzle of astrophysics, it is a monumental test of our own creativity, pushing our machines and our minds to their absolute limits to glimpse the universe's first dawn. This cosmic dawn was not a gentle awakening for every potential galaxy in the universe. The same ultraviolet radiation that cleared the cosmic fog may have also strangled the next generation of stars in their cribs. This is our 10th mystery, the profound and paradoxical impact of reionization on early galaxy formation. Imagine a fledgling cloud of gas slowly collapsing under its own gravity, poised to become a new, small dwarf galaxy. Then, a wave of intense ultraviolet radiation from a nearby, brilliant galaxy washes over it. This radiation does not just ionize the gas, it heats it to temperatures of tens of thousands of degrees. This superheated gas becomes energetic and turbulent, making it incredibly difficult for it to cool down, condense, and form new stars. In the most extreme cases, the radiation can blast the gas away entirely, a process astronomers call photoevaporation. It is like a gentle campfire trying to ignite while a blowtorch is aimed directly at its kindling. This is the concept of reionization feedback, a classic cosmic case of negative feedback. The very process that made the universe transparent may have made it much more difficult for the smallest galaxies to form thereafter. The critical mystery is determining the net effect of this violent transition. Did reionization effectively act as a universal regulator, shutting down the formation of countless small, dwarf galaxies? This would have profoundly shaped the entire future hierarchy of the cosmos, explaining why we see a certain distribution of galaxy sizes today. Perhaps only the galaxies that formed early, before the ultraviolet background became too intense, or those that formed in exceptionally dense, protected pockets of gas, managed to survive and grow. The alternative is a more nuanced picture where this feedback was a temporary setback, merely slowing down the birth of new small galaxies rather than stopping it completely. Solving this mystery is crucial as it forces us to ask a fundamental question about our cosmic home. Is the galaxy population we see today a direct result of this ancient universal upheaval? The answer lies in counting the faintest, smallest galaxies from this epoch, a task now falling to the James Webb Space Telescope. By comparing the number of tiny galaxies from just before, during, and just after reionization, we can finally weigh the true cost of the universe's great enlightenment. The violent deaths of those first stellar giants hold the key to our very existence. These population 3 stars, forged only from hydrogen and helium, were the universe's original alchemists. In their furious cores and final, cataclysmic supernova explosions, they fused the primordial soup into the first heavy elements, the very stuff that would one day form rocky planets, oceans, and life itself. This leads us directly into our 11th mystery, the hunt for the remnants of these cosmic pioneers. We have never seen a population 3 star directly. They remain ghostly theoretical figures, their brilliance lost to time. So how can we possibly prove they were real? Astronomers have turned to cosmic forensics, searching for their chemical fingerprints in the oldest stars still shining in our galaxy. Imagine our Milky Way as an ancient archaeological site. The oldest, most metal-poor stars are like fossilized bones, preserving the chemical composition of the gas from which they formed. If we find a star with a spectrum completely devoid of any elements heavier than helium, it would be a smoking gun, a direct descendant of a cloud polluted by only a single population 3 supernova. Yet, despite decades of searching, no such pristine star has ever been found. Every star we have ever observed, no matter how ancient, has at least a trace of heavier elements. This profound absence tells its own story. It suggests that the first stars lived and died in a frenzy, polluting the cosmos so quickly and thoroughly that the second generation of stars was already born from enriched material. The hunt has therefore shifted. Now, scientists look for the unique chemical patterns left by different types of population 3 supernova explosions. Did a star of 200 solar masses collapse directly into a black hole? Or did it explode in a uniquely powerful pair instability supernova that scattered its specific elemental signature across space? Finding a star with that exact, peculiar mix of elements would be like finding a fossil with a distinct skeletal structure, finally confirming the existence of a creature we have only dreamed of. This search is a race against time, a quest to find the fading fossils of the celestial beings whose light first began to tear apart the cosmic dark. This ancient afterglow holds a secret imprint of the universe's great awakening. The cosmic microwave background radiation, that faint whisper of heat from the Big Bang, is more than just a uniform glow. It carries a subtle pattern of polarization, a specific direction to its light, and this pattern is our 12th great mystery. When the first stars and galaxies flooded the universe with ultraviolet light, they did not just heat the gas, they created a vast sea of free electrons, atoms that had been stripped of their companions. These free electrons then scattered the light of the cosmic microwave background in a process called Thomson scattering. This interaction left a unique, permanent fingerprint on the polarization of that ancient light. It is like finding the faint, fossilized ripples in a pond, evidence of a long-vanished stone. Sophisticated experiments like the Planck satellite were designed to read this fingerprint. By meticulously mapping the polarization across the entire sky, scientists can measure what they call the Thomson scattering optical depth. This complex term is essentially a single number that tells them the total number of free electrons the CMB light encountered on its journey to us. From that number, they can work backwards to estimate when, on average, reionization happened. The mystery deepens because this cosmic clock seems to be telling a different time than other witnesses. The Planck data suggests that reionization was a relatively late and rapid event, largely complete by the time the universe was around 550 million years old. Yet, when we look at the light from some of the most distant quasars, their shadows suggest patches of neutral hydrogen existed earlier than that, pointing to a more gradual, drawn-out process that began much sooner. Reconciling this timeline is one of the most active battles in cosmology today. Is our interpretation of the CMB polarization subtly wrong, or are the quasars showing us only a Chinese letter picture, a single thread in a much larger and more complex tapestry? The answer will force us to rewrite the story of how quickly the cosmic dawn finally broke. The invisible architecture of the cosmos may have orchestrated the entire reionization era. Dark matter, the mysterious, unseen substance that outweighs all normal matter 5-1, provided the gravitational scaffolding for the first stars and galaxies to form. Without its immense, invisible pull, ordinary gas would have remained a formless, drifting haze, never collapsing into the brilliant beacons that lit up the dark. This leads us to a profound 13th mystery. Did the fundamental nature of dark matter itself dictate the pace and pattern of the universe's great transformation? Most cosmologists work with the assumption of cold dark matter, where particles move sluggishly. This model allows tiny structures, the smallest dark matter halos, to form very early on. These minuscule halos could have anchored the first faint dwarf galaxies, creating a vast, widespread population of ionizing sources that got to work quickly. But what if dark matter was warm, consisting of faster-moving particles? This single change would have dramatic consequences. Warm dark matter would wipe out the smallest clumps, suppressing the formation of the very tiniest and most numerous dwarf galaxies. Without this legion of small contributors, reionization might have been delayed by hundreds of millions of years, waiting for larger, rarer galaxies to slowly build up and finally produce enough radiation. The timeline of reionization then becomes a crucial test. If future observations confirm that the process began extremely early, it would be a powerful vote for cold dark matter and its rich ecosystem of small halos. If, however, the evidence points to a later, more sluggish dawn, it could be our first real hint that the dark universe is warmer than we thought. We are using the ghostly aftermath of the first light to probe the properties of a substance we cannot see, touch, or directly detect, turning the story of cosmic enlightenment into a key for unlocking one of physics' greatest secrets. The universe's great transformation did not fade away. It reached a final, dramatic crescendo. Our 14th mystery asks what or who delivered the finishing blow to the cosmic dark ages. What finally forced the last stubborn pockets of neutral hydrogen to surrender their electrons and complete the epoch of reionization? One compelling answer lies in the geometry of light itself. After hundreds of millions of years, the growing ionization bubbles finally began to overlap on a universal scale. The last isolated islands of neutral gas were surrounded, their defenses overwhelmed by the combined radiation from countless galaxies on all sides. It was a cosmic pincer movement of light, yet this simple picture of merging bubbles may not be the full story. There is growing evidence that a new kind of galaxy entered the scene. These were not the first fragile dwarfs, but brighter, more massive, and more efficient stellar factories. Their intense ultraviolet output could have acted like a cosmic scalpel, precisely targeting and evaporating the densest, most resistant knots of hydrogen that the earlier, more diffuse radiation had failed to clear. The light from the most distant quasars provides our key piece of evidence. Their spectra tell us that the vast majority of the universe's hydrogen was ionized by the time it reached a redshift of around 6, a specific point in its expansion history. This marks the official end of the reionization era, but the final moments remain shrouded in uncertainty. Were these last neutral patches hiding in the profound emptiness of cosmic voids, or were they stubborn filaments within the great cosmic web? Identifying the specific sources responsible for this cosmic finale is crucial. Why did reionization not just continue indefinitely? The answer may lie in a fundamental shift in the universe's ecology. Perhaps the very first, most massive stars had all died out by this time, and the galaxies that remained had settled into a more stable but still potent rhythm of star formation. Maybe the remaining hydrogen was so diffuse that it took far less energy to keep it ionized, turning a dramatic revolution into a quiet, sustained peace. Understanding this endpoint is not just about a finish line. It is about discovering whether the universe's enlightenment was declared by a final, brilliant flash, or by the slow, inexorable sigh of the last darkness dissolving into light. Deep within the faint hiss of cosmic static lies a ghostly melody waiting to be heard. This is the 21-centimeter radio signal, a whisper emitted by the neutral hydrogen gas that once filled the entire universe. Every single atom of this primordial substance was, in a sense, singing a song of the Dark Ages. The mystery is whether we can build an instrument sensitive enough to finally tune it in. When a hydrogen atom's single electron spontaneously flips its spin, it releases a tiny burst of energy at this exact, predictable wavelength. For hundreds of millions of years, the cosmos was humming with this universal tone. Then came the fires of reionization. As the ultraviolet radiation flooded through space, it stripped the electrons away, and one by one, the singers fell silent. If we could somehow map this signal across cosmic time, watching as the grand chorus of hydrogen was systematically muted, we would have our ultimate prize, a three-dimensional movie of the reionization era itself. We would see the first ionization bubbles flicker on as patches of radio silence, then watch them grow and merge until the entire cosmic symphony faded away. This is the driving dream behind colossal projects like the Hydrogen Epoch of Reionization Array, or HERA, and the Future Square Kilometer Array. These are not single telescopes, but vast fields of radio antennas spread across deserts, working in concert to act as one colossal ear aimed at the dawn of time. They are not looking for light, they are listening for a shadow, for the precise absence of a signal that tells the story of light's ultimate victory. The challenge is almost beyond comprehension. The signal they seek is unimaginably faint, 1,000,000 times weaker than the radio noise from our own galaxy and every human-made transmitter on Earth. It is like trying to hear a single snowflake land in the middle of a roaring rock concert. Isolating that cosmic whisper requires not just incredible engineering, but brilliant data processing to digitally subtract the cacophony of the modern universe. Success would be the holy grail, transforming our understanding from a collection of scattered clues into a direct, witnessed history of the universe's greatest transformation. But the story of cosmic ionization did not end with hydrogen. A second, more demanding act was still to come, focused on a different character in the primordial cast. This is our 16th mystery, the reionization of helium. While hydrogen, with its single electron, was relatively straightforward to strip, helium atoms held onto their two electrons with a much stronger grip. To tear away that second electron required photons of far greater energy, the kind only produced by the most extreme objects in the universe. This task fell almost certainly to quasars, those brilliant cores of active galaxies powered by supermassive black holes. Their radiation is harder, richer in the high-energy X-rays needed to assault the stubborn helium nuclei. Pinpointing when this second wave of ionization occurred is a complex puzzle. Evidence from the absorption lines in quasar spectra suggests that helium reionization was largely complete by the time the universe was about 2 or 3 billion years old, a full 2 billion years after hydrogen reionization ended. But how did this later phase affect the intergalactic medium itself? The influx of this even more energetic radiation would have delivered a second, tremendous heat wave, reheating the cosmic gas to temperatures far higher than those from the first hydrogen reionization. This reheating had a profound effect, fundamentally altering the structure of the cosmic web. By making the gas hotter and more puffed up, it became harder for it to collapse into the dense filaments that feed the growth of new galaxies. In this way, the late blooming power of quasars may have acted as a cosmic thermostat, regulating star formation for eons to come. Understanding this second wave is crucial because it marks a fundamental shift in the universe's power dynamic. It signals the moment when quasars, the products of mature galactic centers, began to dominate the cosmic energy budget, their fierce glare taking over from the collective starlight that had first cleared the fog. The mystery of helium reionization forces us to see the cosmos not as a place that underwent a single transformation, but as an entity in a state of perpetual change, where the balance of power between different celestial forces is constantly and dramatically evolving. Yet the absence of these small galaxies presents a puzzle of its own. Our 17th mystery confronts the missing satellite problem. The most successful model of our universe's structure, cold dark matter theory, makes a very specific prediction. It says that thousands of small dark matter halos should have condensed in the early universe, and that hundreds of these should now be orbiting large galaxies like our own Milky Way as dwarf satellite galaxies. But when we look, we only find a few dozen. Where are all the rest? A compelling and dramatic solution points directly to the reionization era. The intense ultraviolet background that filled the universe after the first stars ignited may have been a double-edged sword. While it cleared the cosmic fog, it could have also sterilized the smallest potential galaxies. Imagine a tiny, fragile clump of dark matter holding onto a wisp of gas. It lacks the strong gravitational pull of a larger galaxy. When the searing wave of UV radiation from reionization swept over it, that delicate gas was heated to extreme temperatures. In many cases, the gas became so hot and energetic that the tiny halo's weak gravity could no longer hold onto it. The lifeblood of future stars was simply boiled away and blown back into intergalactic space, a process called photoevaporation. In other cases, the gas was not lost entirely, but was heated so thoroughly that it could no longer cool down and collapse to form stars. The result was the same, a dark matter halo that was rendered permanently dark, a ghost galaxy that never shone with a single star. This theory elegantly suggests that reionization did not just shape the light, it also shaped the darkness, leaving behind a population of invisible dark matter halos that still orbit our galaxy to this day, completely undetectable by their absent starlight. The profound mystery is whether this cosmic culling was the primary solution to the missing satellite problem, or merely one contributing factor among many. Did the dawn of light truly leave a legacy of shadows, silencing an entire chorus of potential galaxies before they could ever sing? These first stellar explosions were cosmic alchemists, forever changing the recipe of the universe. When a population 3 star reached the end of its brilliant, short life, it did not fade quietly. It died in a supernova of unimaginable power, blasting newly forged elements out into the void. For the first time, the pristine cosmic gas, which had been a simple soup of hydrogen and helium, was polluted with heavier atoms. Carbon, oxygen, and even iron were scattered like cosmic seeds. This chemical enrichment was a revolution as profound as the birth of light itself. It meant that the next generation of stars would form from fundamentally different material. Gas laced with these metals can cool far more efficiently than pure hydrogen and helium. As it cools, it can condense into denser clumps, fragmenting more easily to birth not just massive giants, but smaller, more stable stars like our Sun. The entire process of star formation became more efficient and diverse. The central mystery is tracing the precise signature of these first polluting explosions. Did a star of 150 solar masses collapse in a way that produced mostly oxygen and magnesium? Or did a true behemoth of 250 suns undergo a pair instability supernova, leaving a unique fingerprint of elements that we could still find today in the oldest stars of our galaxy? The speed of this pollution is another enigma. How quickly did the shrapnel from a single supernova mix with the surrounding gas? If it spread slowly, then pockets of the universe could have remained pristine for longer, perhaps allowing a few last pure population 3 stars to form in isolated regions. If it spread rapidly, then the era of these mythical, metal-free stars was breathtakingly brief. This chemical pollution did not just enable new kinds of stars, it directly influenced the Great Reionization. Metal-rich stars form more efficiently and in greater numbers, potentially leading to more galaxies and more ionizing photons. Yet, metals also make gas more opaque, which could have trapped radiation within galaxies, lowering the escape fraction. The first supernova set in motion a complex feedback loop, where the very pollution that helped build galaxies might have also changed the rules for how their light could escape. We are quite literally made from the ashes of those first violent deaths. Every atom of oxygen you breathe and every speck of iron in your blood was forged in a star that lived and died long before our sun was even a dream in the cosmic dark. Even our most powerful telescopes face a cosmic blind spot. When astronomers point the James Webb and Hubble at the edge of the observable universe, some of the most ancient galaxies simply vanish from view in certain wavelengths of light. They are not gone, they are being hidden by the very fog we are trying to study. This phenomenon is known as the Lyman break, and it is our most effective tool for finding early galaxies, while simultaneously revealing the stubborn remnants of the neutral universe. Here is how it works. Young, hot stars in these primordial galaxies blaze with intense ultraviolet light. But as this light travels toward us, it encounters the lingering patches of neutral hydrogen gas from the reionization era. This gas acts like a cosmic filter, completely absorbing a very specific high-energy part of the galaxy's spectrum. To our telescopes, it looks as if the galaxy's light abruptly drops off or breaks at that point. It is like trying to see a distant lighthouse through a thick, patchy fog. Sometimes the beam shines through a clear patch and we see the galaxy in all its glory. Other times, the fog bank is too dense and the light is swallowed, creating a dropout in our observations. The profound mystery is that these dropouts are not random. They are the spectral signatures of the very last islands of neutral hydrogen, the final holdouts against the tide of ionizing radiation. By meticulously mapping where these hidden galaxies are located across the sky, astronomers can actually chart the geography of the reionization battlefield. They can identify the vast, opaque regions where the cosmic fog persisted the longest. Why did some parts of the universe remain cloaked in neutral gas for hundreds of millions of years longer than others? The answer lies in the large-scale structure of the cosmos itself. Perhaps these were immense cosmic voids, regions so empty of galaxies that there were simply no nearby sources of ultraviolet light to clear them out. Or maybe they were exceptionally dense knots in the cosmic web, where the hydrogen was so thick that it took far longer for radiation to burn through. Each missing galaxy is not a failure of observation, but a crucial data point. It tells us that right there, at that specific point in space and time, the universe was still dark. The pattern of these shadows reveals that reionization was not a uniform curtain lifting, but a fragmented and chaotic retreat, leaving behind a scattered archipelago of darkness that slowly, one by one, finally dissolved into light. Those brilliant quasars, shining with the light of a trillion suns, present us with a timing problem of cosmic proportions. Our 20th mystery asks how the supermassive black holes at their cores could possibly have grown so large so fast. We observe these gravitational monsters weighing billions of times the mass of our sun, blazing away when the universe was less than 1 billion years old. For them to reach such staggering sizes in such a narrow window of time, their initial seeds must have been planted almost immediately after the first stars flickered on. So what were these seeds? One leading theory points to the corpses of the very first stellar generation. When a truly massive population 3-star, 100s of times heavier than our sun, reached the end of its life, it may have collapsed directly into a black hole of perhaps a few hundred solar masses. This would provide a substantial head start. Another, more dramatic idea is direct gas collapse. In the dense, chaotic cores of the first protogalaxies, immense clouds of gas might have collapsed under their own weight so violently that they skipped the star formation stage entirely, condensing directly into a massive black hole seed thousands of times the mass of our sun. A third possibility is a slower, more brutal path where smaller black holes from the first stars repeatedly smashed together and merged, building up mass over generations. Each of these origins leaves a different fingerprint on the reionization story. A black hole born from a single, colossal star would be intimately tied to the ionizing radiation that star produced in its life. One formed from direct gas collapse would ignite in an environment already being shaped by that first light, and these growing black holes were not passive residents. As they fed, their ferocious radiation would have joined the chorus of reionization, their high-energy X-rays and ultraviolet light helping to heat and clear the cosmic fog around them. The formation of the first black holes and the illumination of the universe are two strands of the same cosmic rope, twisted together from the very beginning. Unraveling the origin of these dark seeds is therefore essential. It forces us to ask whether the universe's first light and its ultimate darkness were born from the same catastrophic events. Buried in the faint static of the cosmos is a single, universal note that could rewrite our entire cosmic history. This is the global 21-centimeter signal, a whisper that is not a map but an average, a single data point representing the entire sky at a moment in the deep past. It is the ultimate summary of the cosmic dawn, a single number that could tell us the average temperature of all the hydrogen gas in the universe at the time the first stars began to shine. The quest to hear this note is one of the most technically daring and controversial in all of modern cosmology. A project known as the Experiment to Detect the Global Epoch of Reionization Signature, or EDGES, made global headlines when it announced it had found this ghostly signal. But the signal they detected was not just faint, it was profoundly strange. It was an absorption dip twice as deep as any standard model of cosmology could explain. This was not just a whisper, it was a scream from the early universe that defied all expectations. To create such a strong signal, the primordial hydrogen gas would have had to be significantly colder than our models predict, or the first starlight bathing it would have had to be far more intense. Neither of these options fits neatly into our established story of cosmic evolution. This is where the mystery plunges into the truly exotic. Some theorists suggest that the only way to cool the early hydrogen gas so dramatically is through an interaction with something completely unknown. They propose that cold, dark matter particles, the universe's dominant but invisible substance, might have been colliding with normal hydrogen atoms, siphoning away their thermal energy and chilling the cosmic gas to temperatures physics cannot otherwise account for. If this interpretation is correct, then the EDGES signal is not just a clue about the first stars. It is our first direct experimental hint of how dark matter interacts with the ordinary matter that makes up our world. The scientific community remains intensely divided, caught between the thrill of a potential revolution and the sobering possibility of a simple, earthly error. The signal is buried in a sea of radio frequency interference from our own satellites, from the galaxy, even from the ground beneath the antennas. Is that deep dip the voice of the cosmic dawn, or is it a subtle mimic, an artifact of the instrument itself, or a local contaminant that has fooled us? The resolution of this mystery now rests with a new generation of experiments being built in the most radio-quiet locations on Earth, from the deserts of South Africa to the outback of Western Australia. They are all listening for that one note, a single tone that holds the power to either shatter our understanding of the universe's first light, or to reveal a hidden conversation between the light we see and the dark we cannot. The very fabric of space may have held a hidden force guiding the universe's transformation. This is the 22nd mystery, the role of cosmic magnetic fields. Did these invisible lines of force exist from the very beginning, woven into the cosmos at its birth, and did they subtly shape the entire reionization era? The magnetic fields that permeate modern galaxies are powerful, but their ultimate origin is one of astrophysics' great unknowns. One compelling theory suggests that the infant universe was filled with incredibly weak seed fields, primordial imprints from the Big Bang itself. These initial fields would have been unimaginably faint, a ghostly presence in the formless dark. Then came the first stars and galaxies. As vast clouds of gas collapsed and began to spin, these weak seed fields would have been stretched, twisted, and dramatically amplified, much like a tiny, tangled thread can be drawn out into a long, strong rope when pulled. This process, known as dynamo amplification, could have built the magnetic foundations of the cosmos concurrently with its first light. But how could these invisible fields have influenced reionization? Their effect would have been subtle yet profound. Magnetic fields can influence how gas collapses to form stars. They provide a form of cosmic pressure, supporting gas clouds against their own gravity and potentially slowing down the birth of the very first stellar giants. This could have dictated the initial pace of the cosmic dawn. Furthermore, these fields act as channels and traps for high-energy particles. They could have guided the propagation of the first cosmic rays, focusing their energy and influencing how they heated the surrounding hydrogen gas. This background heating could have made it slightly easier or harder for ultraviolet radiation to finish the job of ionization, subtly shifting the timeline of the entire process. The central mystery is finding any observational evidence for these primordial fields. One tantalizing clue comes from the cosmic microwave background. If sufficiently strong magnetic fields existed in the very early universe, they would have left a unique, twisted signature in the polarization of this ancient light. So far, searches for this imprint have come up empty, telling us that any primordial fields were exceptionally weak. Another method is to look for the faint Faraday rotation of radio waves from distant quasars. As this light travels through the magnetized intergalactic medium, its polarization angle rotates. By measuring this rotation in the light from the most distant quasars, we can probe the magnetic fields that existed during the reionization epoch itself. Proving that these fields were present and measuring their true strength is like trying to hear the faintest possible hum underlying a symphony of cosmic explosions. Did this magnetic whisper gently steer the flow of gas and radiation, leaving a hidden fingerprint on how the lights came on across the cosmos? The hunt for a cosmic missing link has led astronomers to a truly bizarre theoretical creature, the direct collapse black hole. This would be no ordinary stellar corpse. It is a hypothetical giant born not from the death of a star, but from the direct, catastrophic collapse of an immense primordial gas cloud. In the dense, chaotic cores of the very first protogalaxies, a cloud containing tens of thousands of solar masses of pristine gas could have simply buckled under its own immense weight. It would have skipped the star formation stage entirely, vanishing from the visible universe and leaving behind a massive black hole seed, thousands of times heavier than any star-born remnant. Such a monster would be the perfect solution to our supermassive black hole timing problem, providing a colossal head start for growth. But how do you find an object that, by its very nature, is defined by an absence of light? The search is now focused on a unique and fleeting signature. Before the final collapse, this colossal gas cloud would have glowed with an intense, peculiar light. Unlike a star, which is powered by nuclear fusion, this cloud would have shone from the sheer gravitational energy of its infalling material, a process so violent it would have produced a tremendous amount of ultraviolet radiation. Crucially, because no nuclear fusion was occurring, the cloud would have contained virtually no heavy elements. This combination, a brilliant ultraviolet source with no chemical pollution, is the unique fingerprint astronomers are desperately seeking with the James Webb Space Telescope. They are scanning the early universe for objects that are luminous yet spectroscopically pristine. Finding even one would be a monumental discovery. It would confirm a new, primordial path to creating cosmic giants. The deeper mystery is just how common these events were. If direct collapse black holes were widespread, they would not only have been the seeds of future quasars, but they themselves, in their brief, brilliant collapse phase, would have been potent sources of ionizing radiation. Each one could have blasted out a significant amount of the ultraviolet light that helped clear the cosmic fog, making them silent partners in the reionization of the universe. Their story is one of ultimate gravitational surrender, a shortcut to darkness that may have been a vital spark in the cosmic dawn. The cosmic microwave background is our most pristine baby picture of the universe, a snapshot of its infancy. Yet this image was subtly altered by the light of the first stars and galaxies, its fine details blurred by the very process of reionization. This smearing effect is our 24th mystery. As the universe filled with free electrons from ionized hydrogen, these particles became a sea of tiny mirrors. When the ancient CMB light, already on its journey for hundreds of millions of years, encountered this electron fog, it was not absorbed. Instead, many photons were gently scattered, bounced onto a slightly different path. This process, known as silk damping, acts like a soft focus filter on a camera lens. It smooths out the smallest, finest wrinkles in the CMB's temperature map. Those tiny wrinkles are crucial because they represent the seeds of all future structure, the microscopic hills and valleys of density that would one day grow into galaxies and clusters. By studying the precise amount of this blurring, cosmologists can work backwards. They can measure how many electrons the CMB photons encountered, which tells them the total number of free electrons produced during reionization. This gives them that critical number, the optical depth, which acts as a clock for the entire epoch. But the mystery runs far deeper than a single number. The latest, most precise maps from observatories like the Planck satellite suggest this blurring might not be perfectly uniform across the entire sky. What if the pattern of this smearing holds a secret history? If reionization was a truly patchy and drawn-out affair, with some parts of the universe becoming clear long before others, then the scattering of CMB photons would have been uneven. The blurring effect would be slightly stronger in directions where the reionization process was more prolonged or intense, and weaker in others. Detecting this subtle, directional fingerprint in the oldest light of all would be a monumental achievement. It would transform our understanding from a simple timeline into a complex, three-dimensional history, revealing not just when the universe became transparent, but how the great bubbles of light actually grew and merged across the cosmic expanse. We are learning to read the faintest of scars on the universe's first light, a blur not of imperfection but of profound transformation. Our final mystery does not look back but forward into the waiting dark. The story of cosmic reionization is far from complete, and its next chapters will be written by a new generation of celestial observatories, machines of unprecedented power designed to answer questions we have not yet even learned to ask. The James Webb Space Telescope has already begun its revolutionary work, capturing the faint infrared glow of the universe's first galaxies, yet it is merely the vanguard. The future Nancy Grace Roman Space Telescope will conduct vast, deep sky surveys, not just finding a few ancient galaxies, but mapping millions, allowing us to see the full tapestry of the early cosmos and understand how these first islands of light were distributed. But to truly witness the transformation itself, we must listen. The Square Kilometer Array, a continent-spanning radio telescope, will one day tune its immense ear to the cosmic dawn, aiming to capture the full three-dimensional map of the 21-centimeter signal. This would be our ultimate time machine, letting us watch in real data as the first bubbles of ionized gas flicker on and then slowly, inexorably, merge to fill the universe with light. And beyond even that lies a concept like LUVOIR, a giant space-based observatory that could directly image the atmospheres of exoplanets and perhaps finally capture the fleeting light of a population 3-star cluster. With such tools, we could move from inference to direct observation. We could watch the escape fraction in action, seeing how radiation punches its way out of galactic cradles. We could witness the precise moment a direct collapse black hole seed ignites. The ultimate mystery these telescopes will solve is the one we cannot yet articulate. Every time humanity has built a new eye on the cosmos, it has discovered something that shattered our previous understanding. What if the reionization story we have so carefully pieced together is fundamentally wrong? What if an unknown force, a forgotten player, was the true architect of the cosmic dawn? These future observatories hold the power to not just answer our current questions, but to reveal an entirely new set of mysteries, rewriting the very first chapter of our cosmic history. And there you have it, 25 profound mysteries that shroud the Cosmic Reionization Era in intrigue. We have journeyed from the ghostly giants of population 3 stars to the final, stubborn islands of darkness, tracing a revolution that forged the very nature of our transparent cosmos. This was not a single event, but a cascade of interlocking puzzles where the first light, the first atoms, and the first black holes were all inextricably linked. The story of how the universe woke up is the story of how everything we know, from the galaxies in the sky to the atoms in our bodies, first came to be. What is truly thrilling is that we are living through the golden age of answering these questions. Our tools are no longer just theories, but real data streaming in from engineering marvels like the James Webb Space Telescope, providing clues about this ancient epoch faster than we can often interpret them. The story is far from over. It is being written right now with every new observation, every faint smudge of light from the edge of time. So we turn the final question over to you. Which of these 25 cosmic riddles captures your imagination the most? Was it the hunt for the first stellar leviathans, the silent chorus of invisible dwarf galaxies, or the ghostly whisper of the 21-centimeter signal? Let us know your thoughts in the comments below. If you enjoyed this journey to the dawn of time, please like this video, subscribe to the channel, and tap the notification bell so you can join us for our next deep dive into the universe's greatest puzzles.